Hello everybody. In this video, we are going to continue solving another problem from LeetCode Stop Interview 150 problem list live. So far, we have solved all the problems up to uh, gas station. If you haven't checked out my videos on those problems, please go to my channel and check them out. Today, let's look at the next one, which is candy. Well, this is categorized as hard, and this is the first time I'm doing a hard problem live. So I'm actually very nervous, but we'll see. Like if it doesn't work out and I cannot figure out a solution, then so be it. But we'll at least get to see how to approach this problem. Okay, so let's read it. There are n children standing in a line. Each child is assigned a rating value given in the integer array ratings. You are giving candies to these children subjected to the following requirements. Each child must have at least one candy. Okay. Children with a higher rating get more candies than their neighbors. I half understood that. Okay, let's continue and say return the minimum number of candies you need to have to distribute the candies to the children with basically these rules, I guess. The reason this is not super clear to me. So they're saying that if we have, I guess it is a higher rating compared to the neighbors, right? So it's not just that in the whole array. So let's actually look at an example. So ratings are 1, 0, 2. There are 3 children and the minimum candies is 5. The explanation is you can allocate to first, second, and third child with 2, 1, and 2 candies. But why? Let's see. So, oh, I see. So I think all of them need to have at least one candy. So if this 0 has one candy, then the neighbor here has a higher rating than 0. So that neighbor needs to have one more. And this neighbor needs to have one more. So that's why 2, 1, 2. Okay, so I think now I understood. So basically the higher rating isn't higher compared to any other children in the line. It just matters next to the neighbor, right? So for example, this 2 does not have to have more candies than this one. So the child at index 2, the only neighbors we care about is index 1 and index 3 there if there was a child there, right? I wish they had given an example with more children, but okay, so that makes sense. So at least now this clarified. And the other thing I noticed is that they have said rating, higher rating, not like equal or higher. And they need to have strictly more, not equal. Okay. So let's look at the second example. Ratings is 1, 2, 2. So there are 3 children again. And in this time, it can be done in 4. I wonder. Okay, I see. Yeah, basically, and yeah, that is where strictly higher is important. But okay. So we can allocate 1 to 1. Yeah, that's because the first child needs to have 1. But the second child with a rating value of 2 needs to have 1 more than that. So 2. But then this person can actually have 1 because yeah, his rating is the same as the this two, and so he doesn't need to have more candies than that too. So that is actually interesting. Like, so he doesn't even need to have equal candies to his neighbor. Only if his rating is more, and then basically we give that child more. Otherwise, it can also be less. If the rating is equal, they can also receive fewer candies, right? So that's interesting. Okay. I think I understand the problem now. So everybody at least gets one, and for every child, the property that has to be true is if their rating is more than their neighbor, the neighbor to the left or right. I guess we need to check both the neighbors. Then they need to have more candies than their neighbors. And I think given the fact that we have to find the minimum number of candies, basically more will be one more, right? We don't want to give more than one more because that wouldn't be the minimum. So, okay, so that's another thing to think about. Okay, constraints are that, okay, n is the same as ratings dot length. Okay, that's fine. And that's the size of the array, which means the number of children is between 1 and 2 to the power 10 raised to 4. So 20,000 children or at least one child inclusive. And then the rating values are between 0 and 2 to the power 10 raised to 4. So that's 0 to 20,000 inclusive. Okay, this is interesting. So let's take an example. here and see what is an approach that will work. I mean, it's a hard problem, so I'm assuming there are like multiple approaches of varying efficiencies. But okay, let's not worry about the hardness of the problem for a minute. So let's say that we have, in this case, 102, right? So in this case, if we just check linearly, right, the ratings. So let's say these are the ratings, or let's say these are the candies we distribute to them. So if we linearly check the ratings, we say, okay, I have 1. What is its neighbor? Its neighbor is 0. Well, we haven't assigned the candies to 0 yet. Okay, so let's say we begin with all 1, right? Because everybody needs to have at least 1 candy. Then we start the processing. So we then evaluate both the R and the C together. Okay, so we say, okay, this person has a higher rating than the next one, so we need to have it 1 plus the next person. So let's say that is 2. Now we look at 0 and we look at both the numbers, right? We look at 0 and 1, and that's lesser, so we don't worry. We look 0 and 2, that's lesser, though, so we don't worry. So we leave it alone with 1. And then we look at 2 and we say, okay, its neighbor is only 0 and it is bigger, so we need to have 1 more than the neighbor, so 2. Well, in this case, it finished in 1 pass, but I'm 100% sure, 99% I guess, that it won't work in 1 pass. So let's try to construct an example where it doesn't work in 1 pass, right? What would it be? So let's say 1, 2, 3, 4, right? Actually, even in this case, it will work with 1 pass because it's increasing. Actually, yeah, let's take a decreasing one. So 4, 3, 2, 1, right? And then let's do the same thing and see. So we start with all ones and then we start our iterations, right? So we say, okay, hey, the first person's neighbor, well, it has a bigger rating than the next one, so it has to have 1 more candy. Yeah, this is a good example. It needs to have 1 more candy than the previous one, but the previous one, the candy value is still 1, right? Which will increase because it's on. Okay, so then the 3, when we look at 3, we say, okay, this side neighbor we are lower than, but that side neighbor we are bigger than, so we need to have 1 more than that side neighbors, and that count is 2. Same with here. This will become 2 because of the one after, and then this will stay 1, right? But this is not the right answer because the reason is because when we computed that the first child gets 1 more than this child, that second child's candy count wasn't up to date because that is going to increase when we look at their neighbors. Okay, so here I guess what we can do is we can do more than 1 iteration, right? Again, probably there is an approach where we don't need to, but let's at least come up with a solution. So let's keep going again, where we say, okay, we'll update this to 3 because it needs to be 1 more than the next one. This needs to be 3. This can be 2, and this can be 1 because, yeah. So that is that. And then we do 1 more iteration and we say this needs to be 4. This will stay 3, this will stay 2, and this will stay 1, right? So yeah, so I think, okay, so here is one algorithm that I think works, is that we keep on doing that until we don't change. Until, like, for example, if we do this 1 more time, right? If we do this 1 more time, it wouldn't change. It will stay 4, 3, 2, 1. So we keep track of whether we changed the candy count. And if we haven't changed it, yeah, then we basically stop, right? Because then we are up to date. Okay, so that approach would work. Obviously, it's O of n squared because we are doing the linear processing n times until it finishes. And in the worst case, like I think this is the worst case where it keeps on decreasing. In the worst case, it will have to do n minus 1 such iteration so that the neighbors get updated enough, right? So, okay, so let's try to implement it. I wonder if it is worth implementing, but yeah, let's try to implement it. I think sometimes it gives us ideas about what is a better approach, right? So candy multiple passes, I guess. Okay. So that's that name. Yeah, with more time, you can always come up with a better name if, yeah. Okay. So let's go a little bit carefully because we have to consider that for some indices, the neighbors on the left might be out of bounds or the neighbors on the right might be out of bounds. So that is one thing we need to care about. we also, yeah, we need a candies array, which is actually, let's do the following, right? So int n equal to ratings dot length. Okay. Actually, in Java, like I've said in some previous videos, like things you don't intend to change the value of after you initialize, it's always good to declare them final, right? So let's make that final, and then let's just use n here. Okay. So we need the candies count. Well, and we need to fill it up with 1, right? Because it initializes to 0. Java does that by default, but we need 1. So that is minimum number of candies. And then what we do is we write a for loop. Well, this is the outer for loop, right? Like how many times are we going? In the worst case, we will need to go n minus 1 or n times. I mean, like, yeah, n times. And outside we'll also need to keep a candy count, so we don't have to count all the time, right? Okay, so let's do that. And in the inside loop is where we do our, like, one pass of updating the whole candy array, right? So that one is the one that goes j equal to 0. I and j are probably not the best names here, but that's okay. We will try to, and the reason they are not the best names in such cases is we tend to write I, and in the inside loop, actually, we need to do j, right? When we look up the ratings and the candies array, we need to look at the j index, but we'll be careful. Anyway, so what do? We look at two neighbors, right? The left and the right. And we look at their ratings and we look at their candy count and see if they are compatible, right? Okay, so let's actually write that. I think there will be some duplicate code for two neighbors, and probably we will move it to the helper, but let me first write that code here. So what do? We say, okay, let's do this. Int rating equals, sorry, not ratings, rating equals ratings of j, right? Int candy equal candies of j, right? So that's the rating and the candy of the current person. Now, if the I minus 1 is in bounds, so I minus 1, again, I think we will need a helper for this, but is greater or equal to 0. Now, since we are going one before, we don't have to check that. And typically, if you check something is in bounds, you have to check both sides, right? I minus 1 is less than n. But in this case, we know we are subtracting and I is within bounds, so we don't have to kind of check this, right? We say if I is greater or equal to 0, then we say, okay, if the current person's rating is greater than the ratings of I minus 1, and current person's candies is less or equals. Remember, it has to be more. So even in case of equals, we need to update it, right? Candy is less or equals candies of I minus 1. In that case, we are going to update candies of j. Oh, see, I made the mistake already. It's actually j minus 1. So we are looking at j. Okay, j. So candies of j, that is what we need to update, right? Well, actually, let's first update in candy because we may have to update for the second neighbor. So then we update candy equal to candies of j minus 1 plus 1, right? Okay, so that's that. And then we repeat that, and that's why I think we'll write it in a helper 1 second. Actually, let's write it in a helper right away, right? So why increase our work? Okay, private void update candy at index, right? It needs ratings, needs candies, needs an index, and it needs the neighbor index. Well, that's a very big, actually, let's call it adjacent index. Okay, and here we say we'll update the variable names 1 second, but We actually here, what we can do is we can actually do a few things. We can actually short circuit, right? So if we say if the adjacent index, and we don't have to worry about index being out of bounds. It's a helper, so we can assume whoever is calling us is making sure of that. But we don't want the helper to make the calling code to have to worry about adjacent index bound checks, and because we'll check it here. That's the whole point of helper, right? We remove duplicate code. So if it is, and here we have to check both sides because we could be called with an adjacent index on the left or the right side, right? So a greater or equal to ratings dot length, then we return. Basically, we break out. If the neighbor's index is out of bounds, we don't have to do any work, right? Okay. Otherwise, otherwise we do this, right? So actually, we can do this also. We can say, or if the rating of the current index is less or equal to the ratings of adjacent index, then also we can return, right? We don't have to do anything in that case. Sorry about that, right? So now we are left with the case where we do have to update it, right? So let's do that. One sec. And here, well, wait. Yes. And then we say, we can do the same short circuiting if it is this one, right? Of course, candies of index and candies of adjacent index. If it is already greater, then also we return. And finally, we can just say candies of index equal to candies of adjacent index plus 1, right? Okay, so let me review this again. So we are given an index, and this function's job is to update the candy count if appropriate at that index corresponding to this neighbor or that adjacent child. So we say, okay, if adjacent child is out of bounds, which is less than 0, and then we return. Otherwise, if our rating is less than the adjacent child, then we return, or equal to even, right? If it is equal, we don't care. Otherwise, if the candies is already bigger, because our rating is bigger if we haven't returned yet, but then the candies is bigger than the adjacent, then also we return. Otherwise, we update our candies. Okay, I think this works. And let's now just call this helper. I think now I don't even need, yeah, I think I can do this, right? So we say update candy at index. Wait, we have to pass ratings, candies, j, and j minus 1. This is actually cool because now the code also becomes very readable. It's saying, hey, update based on j minus 1, update based on j plus 1. The helper is doing bounce check, so we don't have to do the bounce check. Okay, so that is one pass. Well, actually, okay. So what we also need to do is new candy count equal to 0. We kind of need to figure out what the updated candy count is, right? So after we have updated a cell, we say new candy count plus equals, and we say candies of j, right? And outside the loop, we will know that after one pass, what is the total candy count? And if that has actually, this one cannot be 0 because remember the candies array is already filled with 1. So that is going to be equal to n, right? And here we say, okay, if new candy count is equal candy count, then we return. If we haven't updated anything in this iteration, then we just are done, right? Otherwise, we say candy count equal to new candy count, right? Something has changed, right? It would have only increased, but something has changed, and so we update it. And here we say return candy count. So after a bunch of iterations, in the worst case, now the reason this could have been a while true loop, if you think about it, this for loop here, because at some point this will break out of the loop. Not return, actually, this is a break, by the way, sorry. So at some point this break will break because at some point we will not update our candy count unless we have a bug, in which case while true would go infinite. So anyway, but it is a good idea to bound our number of times we are doing the inner loop. So anyways, that's why we did that. Okay, let's try to run this and see here. I mean, I'm 99% sure there is a more efficient approach, but uh, I always try to, implement the approach that comes to mind, and that gives us some ideas. Okay, so let's do that. Let's see what it does. Oh, cool. It did work. Okay, I do want to add definitely the other test case, right? Which is, well, let's add 1, 2, 3, 4, 5 as well, or 1, 2, 3, 4, and let's also add 1, 2, 5, 4, 3, 2, 1, right? Both forwards and backwards. Cool. Actually, that worked really well. Okay, great. So in both cases, it's 10, 4, 3, 2, 1, or 1, 2, 3, 4. Okay, so that's good. I'm actually a little bit tempted to submit it, but I'm going to save some time on that one. I'm pretty sure that that won't work. Okay, so now let's go back to see what we can do differently, right? We are doing so many iterations. How can we avoid it, right? So uh, let's see. Are there ways to? So I'm going to do that. Oh, never mind. 1 sec. Okay, so in this case, what happened is we actually needed a bunch of iterations. Uh, in fact, it is like 4 iterations, right? We started updating here. So 1, 2, 3, 4. So yeah, O of n iterations, right? And okay, so how can the main problem is like it's in decreasing order. So it takes time to percolate from the right side to the left side, right? That the fact that this 2 wasn't updated to 2 here, and that's why the value for 3 only became 2 here, right? Or similarly, this 3 wasn't yet updated to 3, and that's why for the 4 here, we actually said, oh, the candy count is 2. If somehow this 3 was updated, then yeah. So the thing is, I mean, if we went the other way, right to left, then that wouldn't be a problem. But then the problem is the other case would become bad, right? 1, 2, 3, 4 will become bad. So what I mean is, if we went from like right to left, okay, let's try that, okay? Let's say we were going right to left. Actually, let me just copy this much. Okay, so that is still our beginning. Okay, so if we went from right to left, then what will we end up doing? We'll end up doing, uh, let me just 1, 1, 1. So what will we update? So we'll first update this to 2, then we'll update this to 3, and then we'll update this to 4 correctly, right? Because we are processing the last index first, and we're saying, oh, is it bigger than its neighbor, the rating? No, so we leave it alone. Then we process the second last index, and we say, oh, it has a higher rating than its neighbor, let me make it +1 compared to this neighbor. On that side, it's lower than its neighbor, so let me keep it as it is, as it is too, and so on. So in one iteration, we'll update it. But in this case, the problem is if we switch doing that instead of left to right, we are going to make this a bad case. 1, 2, 3, 4 a bad case, right? Because now what happened is the bigger number is on the other side. So that won't work. What about like a case like this actually? 1, 2, 3, 4, 3, 2, 1. Yeah, I think this is the worst case, right? Either like this side doesn't work or that side doesn't work, and I think worst case as in it's a worse based on the algorithm we are thinking of. Okay, actually, oh wait, okay, so what if we make one pass from left and one pass from right? Yeah, that should work, right? So for example, in this case, let's do that. Let's do that. So initially, they're all ones, okay? So let's make one pass from left to right. Okay, so what does that do? And actually, in that case, we don't even have to look at both the neighbors. We can just look at the previous neighbor, right? When we are going left to right, we just say who is to our left, who is to our left, because the right side will be updated in the second pass. So okay, so nobody is to the left of the first dude, so the he stays as it is. This will become a 2 because the rating for this person is bigger than the rating on the left side, so we need to update it. Similarly, this becomes a 3, this becomes a 4, but this stays a 1 and a 1 and a 1, right? Because the rating for 3 is lower than 4, or it's not bigger, so we leave it alone. We still haven't updated 3 compared to 2, which is on the other side, but that's what we do in the second pass, right? So we say, okay, so we say this, right? Now we do the other way around. So when we do the other way around, let me copy this array and then update it. Okay, so we are going from right to left. We're saying, okay, nobody's to the right of the last person. So let's go to second last. So what is their rating? Their rating is 2 compared to 1. So that needs to be updated to 2. And their rating, the third last rating is 3, and that is bigger. So that needs to be updated to 3. This 4, yes, its rating is bigger, but the candy count is already bigger, so we don't care. And then we continue and nothing will change. So yeah, I think this seems to work. So that gets rid of the redundant iterations. Okay, I believe it does. I'm not sure if I mix and match like ups and downs and local peaks, whether I think it will still work, because basically we are percolating the candy count from the left to right, and it will fully percolate, and we are percolating the candy count from yeah, left to right and right to left, right? And I think that will, two sweeps will work. So okay, so let's say candy 2 passes, for lack of better name again. I think that's a reasonable name actually. Ratings, okay. So here we are doing 2 passes. We still need a candies array. Candy is equal to new. Let's also have that n that was there. In this case, though, I'm not sure if we need it multiple times, but anyway, it's ratings dot length, the new int of n, right? Okay. And we need to fill the candies array with 1. Okay. And then we do 2 passes. So this is a left to right pass. And there we can start with index 1, right? Int I equal to 1, because 0 doesn't have a neighbor. I is less than n plus plus I. And there we just look up I minus 1, right? Actually, we can just call our update helper. In this case, though, the bounds check is not necessary that update helper does, because we know it will be in bounds, but it's okay. I don't think it will, oh, not that one. I don't think it will really hurt the performance. Okay, so let's, yeah, here we say update, pass it ratings, pass it candies, pass it I, and the I minus 1 neighbor, right? The one on the left. Is that it? 1 second. Do we do anything else? No, I don't think so. Okay. And then we do another right to left pass, right to left pass. And we say for int I equal to n minus 2. Remember, n minus 1 is the last index. And that doesn't have any neighbor on the right side. So we start at n minus 2. And whenever we do such a thing, it's always good to make sure that what if the value of n is such that that becomes something invalid. But I think in this case, you will see why that actually just works, and you won't need like an extra check. So for example, let's say if n is equal to 2, then I is equal to 0. And n equal to 2 means it's an array of size 2, right? There are 2 children. And I is equal to 0, and that makes sense. There is 0 and 1, and 1 doesn't have a right neighbor, so we will start at 0, and that's good. If n is 1, which is a valid n number based on the constraint they have given, which means there is only one child, then I will start at minus 1. But this check of for loop will basically make the for loop not run at all. Remember that this part of for loop is always checked, even on the first iteration, right? The condition. Okay, so that works. And we will call our same helper ratings, candies, I, and I plus 1, right? So at this point, the candies array should be updated with the, well, so now we need to sum up all the candies. So int candy total equal to 0 for I equal to 0, I is less than n plus plus I. Actually, n was useful. Okay, candy total plus equals candies of I. A single line for loop, you don't need brackets, but okay. Breton candy total. There you go. Oh, I haven't called it from here yet. 1 second. candy 2 passes. Somehow I never selected the right one. Okay. This works, I'll be really happy. Cool. It worked without compilers, which actually is good. Like that makes me feel good. Okay, cool. This one I am definitely going to submit and see. Like that definitely runs more test cases as well. So let's see what happens. Oh, cool. So it did get accepted, which is the first order of business. And yeah, it beats about 80% of people in time, which is, I think, great. Probably a lot of them figured out the best approach, which makes sense. And their implementation is very tight, looks like. Okay, cool. Yeah, memory is like, I don't think there is, okay, so if there is, we are so low on memory, I don't know if there is a way to avoid the candies array. I mean, I don't think so because, like, for example, if yeah, I like if we need the candy count of our neighbors, and that individual count matters. So just keeping a total candy count really wouldn't make this algorithm work at least. And what I was thinking is when I kind of interrupted in for a second is that when you have a higher rating, it matters only rating compared to the neighbors. It doesn't matter that you have a higher rating among all of them, right? If that was the problem, if the problem was like, hey, across all the kids with the higher rating needs to get more candies than every other kid that the rating is higher compared to, then the problem is very different because in that case, you can basically, I guess you can sort the whole ratings array and then you can just calculate the candies, right? You can just say 1 comma 2 comma 3 comma 4 comma, it's 1 plus 2 plus 3 plus 4 plus 5 up to if all the numbers were unique, right? Something like that. Anyway, so I think I don't see a way of becoming better at memory, or at least, conceptually speaking, right? So yeah, hopefully that was helpful. I was quite nervous because it was our first hard problem on this channel, but looks like we made it through. If you guys like what I'm doing on this channel, please consider subscribing to my channel and please hit the thumbs up button on the video. See you guys next time.